Another chemistry for BTEC Applied Science AAQ, and this video is about ionization energy. Electrons. What the hell's that about? Well, it should be obvious really. Anyway, atoms are most stable when they have a full set of electrons in their outer shell. When their outer shell is full. Like this lady with her rings here, she's got a ring on each finger, so 8 rings, and she's very, very happy, very, very stable. Okay, the synchronized swimmers, there's 8 of them, and they're in a nice group, and it's all nice and balanced, and everybody knows their place. Okay, like a house of cards is very well built. Okay, so when the outer shell is full, then it's very, very stable. Okay, this is why noble gases are so unreactive. They just don't want to give up an electron. Yeah, they're very happy as they are. Now, ionization energy is the minimum energy needed to remove an electron from a neutral atom. I say it's the first ionization energy. We'll worry about taking more than one electron later on in the video. But the first ionization energy, the minimum energy needed to remove an electron from a neutral atom. So if you look here, there's a lithium atom, and we take away an electron, and we end up with a lithium ion. And this equation, you need to be able to write these little equations. So Li goes to Li plus an electron. Okay. Don't worry too much about what ionization is measured in. Kilojoules per mole. Yeah, we know that energy is measured in joules, and then a mole is just a very large number of atoms. Kilojoules per mole. You can actually ionize some molecules as well, but we'll worry about that in a later video. Now, first ionization energy, how do you think it will vary in the periodic table? Okay, how will it vary going from group 1 to group 0? So from lithium to neon, how will the ionization energy vary? Also, how will it vary? Later on, we're going to talk about how it will vary for different periods as well. But first of all, which atoms do you think it's going to be easier to take electrons away from? And then which atoms would it be very, very hard to take electrons away from? Well, look at this graph. I reckon that in the exam you might be given this graph, and first of all, what patterns can you see? And then we're going to try and explain why. So this is the ionization energies. Again, don't worry about the units. For different elements from hydrogen up to, in this graph, it's going to xenon, although I dare say we only need to know up to krypton, which is 36. So for different atomic numbers, we've got the first ionization energy. Look at the graph yourself. What patterns can you see in the graph? Well, hopefully you will see that Group 1 metals have the smallest ionization energies. So lithium, sodium, potassium, rubidium, cesium. Yeah, Group 1 metals have the smallest ionization energies. Next, noble gases have the biggest ionization energies. So helium, neon, argon, krypton, xenon, they have the biggest ionization energies. So that's group 0. Ionization energies increase as we go from group 1 to group 0. That's the general trend. If we look at group 2 over here, so this is group 2, yes, from lithium up to neon, we see that the ionization energy gets bigger. It doesn't always follow that pattern. There's little anomalies here and there, which we're going to talk about. If we look at period 3, from sodium to argon, yes, the ionization energy from group 1 to group 0 gets bigger. Next, ionization energies decrease from period 1 to period 5 for elements in the same group. So helium, neon, argon, krypton, xenon, they're all in group 0. And going from helium to xenon, we see that the ionization energy gets less. Lithium, sodium, potassium, rubidium, they're all in group 1, but going from period, in this case period 2, yes, to 3, 4, 5, the ionization energy gets less. So those are the patterns. Why? Okay, first one, group 1 metals have the smallest ionization energies. Why? Because group 1 metals only have one electron in their outer shell. If they lose that electron, then they're going to have a full outer shell. So it's going to be quite easy. It won't take a lot of energy to remove that outer electron. It will take some energy, but not a lot. Noble gases have the biggest ionization energies. Why? Because noble gases have a full outer shell. They are very, very stable, very, very balanced. They want to stay as they are. You're going to have to do a lot of work to kind of crack into this full shell. Ionization energies increase from group 1 to group 0. Why? Because going from group 1 to group 0, there are more protons in the nucleus. And these electrons are attracted to the nucleus because positives and negatives attract. And so the more protons there are, the more electrostatic attraction there is to the nucleus. And so you have to do more work to remove the electron. Then ionization energies decrease from period 1 to period 5. Why? Two reasons. I'm going to talk about a bit more in the next slide. Shells act as shielding. Yes, this attraction between the electron and the protons in the nucleus, if you've got shells in the way, then it makes the attraction a bit weaker. Also, as you go from period 1 to period 5, there are more and more shells, and also the electron is further from the nucleus, so the attraction is weaker because the distance is bigger. Just on that last point, if you look at this, lithium, sodium, potassium, they're all in group 1, but can you see why is it going to be easier to take away the potassium electron than it is the sodium? Why is it going to be easier to take away the sodium than it is the lithium? Okay, and you see that the shells act as shielding, yeah, for this electrostatic force. They make it weaker. And also the atoms are bigger so that the distance from the nucleus is bigger. Now, subshells. Subshells have a little effect too. And this is these little anomalies that I was talking about. In period 2, look at these two here. Yeah, you need more energy to take away the S2 electron. Yeah, in periods 2 and 3, the P1 electron is easier to remove than the S2 electron. So the P1 electron, this yellow one here, is easier to take away than that one. Now why? Well, you're not actually cracking into a shell, but you would be cracking into a subshell to take away that S2 electron. So like the subshells have their own stability. Yes, these two electrons in the S subshell, yeah, they're nicely balanced all by themselves and they don't want to be disturbed. Also, if we look in periods 4 and 5, yeah, the P1 electron, which is there and there, is easier to remove than the D10 electron, which is there and there, for the same reason. Okay, because a full subshell is a nice thing to have. It's not quite the super stable thing as a full shell completely, but nevertheless it's not too bad. So the fact that we have subshells means it's a nice stable configuration. And this graph is actually good evidence for subshells. So far, we've just discussed the first ionization energy. Now, what about the second and the third and maybe the fourth? How much energy is needed to remove the second electron, the third, etc.? Well, I'm not going to use a graph for this one. We're just going to look at the numbers, and we'll see the numbers form a nice little pattern. We're going to look at boron. So boron has 5 electrons, and it's 1s2, 2s2, 2p1. So you've got 2 electrons in the first shell, and then 3 electrons in the second shell, which is 2 s1s and a p1. Now, to take away the p1 electron, relatively easy. So that's the 801 joules there. That's relatively easy because it's all on its own. It's all on its own in the shell. No, it's all on its own in that subshell. Yes, which is the p subshell. The next 2 electrons, well, that's a little bit harder because now we're cracking into a subshell, aren't we? So we're trying to break apart the S2 subshell. So that's going to take more work to do. But the biggest change noticeably is when we get to the 4th and the 5th ionization energies, because now we're actually cracking into a whole shell. So notice that there's a big jump when we start trying to take away the 1s2 electrons. Yeah, and that's the 4th and the 5th ionization. So the first electron on its own, dead easy. Yeah. The second and the third electrons, much harder. But then there's a big jump after that because we're diving into a new shell. Okay, it's like a Nobel gas. The first electron in the p subshell on its own, not much energy needed to remove it. The second and third electrons in the 2s subshell, well, they're a bit closer to the nucleus, so they're going to be harder to remove. So it goes up a bit, but then we see a big jump as we're trying to break into a whole new shell. Yes, and it's close to the nucleus and there's no shielding, so you're going to have to do a lot of work to take those electrons away. Just a note there, you know, when, let's say, for example, aluminium is in group 3, and if aluminium takes part in a chemical reaction, it's going to become Al3+. It's going to lose 3 electrons and become a 3+ aluminium ion. Okay, we say that it has a valency or an oxidation state of +3, and that means that when it takes part in a reaction, it loses 3 electrons. Yes, so we've been talking about the energy needed to take away 1 electron and then 2 electrons and then 3 electrons, but in practice, if aluminium or boron, which is in the same group, takes part in a chemical reaction, they're going to lose 3 electrons because they have what we call an oxidation state of +3. So look at those equations that I was talking about. You know, I told you might have to write those equations down. Key points. Know what ionization energy means. Be able to explain the patterns in that graph. Okay, I've waffled on about it quite a bit. Talk about nuclear charge. Yeah, the more protons there are, the more attraction there is. The number of shells, which is going to affect shielding, but it'll also affect the distance from the nucleus. And then the effect of subshells as well. You know, what evidence from this graph is there of subshells, that each shell is made up of different subshells? Okay. Be able to explain how ionization varies when subsequent electrons are removed. In other words, for the first electron, then the second, then the third electron. If you're given the data, be able to explain that data.